moduli, where these E1 and E2 are the distortions along either XY axis or perpendicular to it. So basically it's very similar meaning to the shear, and there's a reason for it. And we define them relative to an axis ratio Q, which is the minor to major axis. And so the way we then compute surface brightness in that case, we define the radius here, which effectively, the way we define it here, means that the overall radius within where we assign it to be a constant surface brightness or outside zero is a product average of the major axis to minor axis. So overall, this type of definition of ellipticity contains the same amount of surface brightness. So it's flux conserving if we distort around with this eccentricity moduli in this definition. So, and now the next thing we do here, this is a block that I want to go through. So we define here a light model, which we call ellipsoid, which is basically this guy here. We define a lens model, which here we have shear and convergence. So we just happen to have split the convergence term and the shear term in two models, but there's also one lens model where you can put them both together. We have a third model for comparison where we just talk about, we wanted these parameters to be defined as the reduced shear, this guy here. So, and now we do the predictions of what's happening. So first, we define a grid in theta. So where we look at the image, we define an ellipsoid. So here first to start, we define it to be E1 and E2 equals 0, means round. So the axis ratio is 1 at the center with a certain radius and the amplitude. That doesn't really matter for illustration. We define a shear, gamma 1 and gamma 2, and a convergence term. So how do we now predict what's going to happen with this ellipsoid when it's getting sheared? First, we compute here the intrinsic source, so without any lensing, which is just in this language, evaluate the surface brightness at these coordinates for the model that we have with this parameters done. That's the flux of the intrinsic no lensing. So how do we compute the lensing effect? First, what we do is we reshoot all the coordinates that we previously here evaluated back in the source plane with the linear parameters with the lens model. And what we get is position in the source plane. So what we get is this guy here. And the next step is we evaluate the surface brightness at these transformed positions rather than in the image plane in this transformed distorted coordinates. And what we get is the flux, how we see it in the image. And that's all. And here we do the same thing with when we just assume that these parameters are the reduced shear and with the same surface brightness. And so if I execute this block here, what we see here is when I put in a round source, that's basically the round case, I see that when I put in this in the lens model, I put these numbers in. I see at one point it's growing by 20%, and it gets distorted around this axis. So if I were to change the sign here, I can execute that as well, and it's getting distorted in the opposite direction. I can also set this to 0 and this guy to 0.2. And what it's going to happen is it's along not the orthogonal, but by 45-degree shifted. I can also change the convergence to be negative. And what's going to happen is that the source is shrinking. While this here in reduced is conserving the surface brightness here, while this is not. So this is for the round initial case. So what if I make first, I turn all the lensing off, just to see, do you believe this guy is round? If they're straight lines, these are all identical. If now I put some ellipticity in the intrinsic source, let's put quite some in. This is a quite high ellipticity. You see the intrinsic source has this shape, length is obviously the same, and so on. So now I have an intrinsic source that is has a shape in this direction, and now I can, for example, put in a shear term that is also high, that happen to be in the other direction. And what you see is that it gets tilted around. So this image is not in the direction of the shear, or no, more in the direction of the shear. Let's put this a bit down. And what you see here now, it's halfway in the direction of where the lensing goes and the intrinsic size. I have an exercise for you, is to try and come up with keep an ellipticity in the source, and try to find a lens mode when lens bound. So, oh, I just saw my internet was unstable. Can you hear me?
Yes, it freezes for a few seconds, but
okay. Okay, so then so the exercise I have for you here is play around for about 10 minutes, setting different parameters for shear and convergence and ellipticity. And one exercise that you could try is make an elliptical source, doesn't really matter in what direction, and find the lensing parameters that will make the source, when it's seen being lensed, look round. Do you understand the exercise? Yeah, just play around 10 minutes to get a bit used to these parameters. You may also go back and see how they're actually defined. And if you have questions, I'm here. And I stop sharing for now. And if someone has a configuration that you put an ellipticity in the intrinsic source, and when lensed, it's round, please share the screen.
No. Bien, profe, su merced, ¿cómo le va?
If you have questions or want to show something? Yeah. Please speak up.
I have a question, Simon.
Yes.
In this case, you have from the source, you can obtain this information about the lensing sources and reduce shapes distortions. Okay, but I think in the observational image, you have first the image and the image of the lensing sources and reduce shape distortions. But how you do to obtain the inverse information?
So the exercise here is basically you can't if you don't know how the intrinsic source is. You always find a certain shape of the intrinsic source that maps with another lensing operator to the same appeared image and shape. And so this is shape noise. You can always find, I can give you an infinite set of different intrinsic combination of intrinsic source and distortions that lead to the same observed shape.
Yes.
And that is shape noise. And that's basically one of the degeneracies that we try to explore here by playing around of how you can change the ellipticity, intrinsic ellipticity of a source and the lensing kernel to come to the same result answer. So the answer is you can't. And what weak lensing does when they just look at galaxies that are some blurry ellipsoids, roughly speaking, what we know luckily about the universe, that on large scales, these shapes are the intrinsic shapes do not know about each other. So they're randomly orientated. And so if you now stack a lot of randomly orientated shapes, you effectively get a round, on average round shape or a random orientation.
Okay.
And so weak lensing basically relies on that assumption, which I think is very valuable, and then measures the shapes and looks for correlation. So if all the galaxy happen to be more, have a measured shape more in one direction over the other on a certain patch on the sky, this is indication that the lensing effect has a certain direction and strength. And that is the primary way to actually use weak lensing as a tool. And we're not talking about 10 of these shapes or hundreds, we're talking about millions of galaxy shapes that one correlates. And in these high numbers, even low signal to noise per object become a significant source of information.
Okay, thanks.
Are defined and what their effect is right away. I start sharing my screen again. So now the next part is a bit theoretical. So there's a box with a lot of like equations, operators. We want to generalize this what we actually have explored here, more or less intuitively or by playing around, by at random or whatever, have that term generalized. I don't go through all of the text, but the basic idea is we can define that an image D at theta looks the way it has a certain source, and the lensing operator here is beta of theta, or we can just write it as theta minus the deflection. So this is beta basically. L of theta is beta, so but we can write it as basically an operator that moves around, maps coordinates. And so in the operator language of lensing, we can write D as effectively the lensing operator acting on a surface brightness. That's a general way to write it down. And now what we effectively done is, if we know the source and we know the lens, we can compute this guy, and that's what we've done, and we end up with an image D. Now I can mathematically expand and just input another operator in between, which is unity. It just doesn't do anything, keeps the coordinate at the same place, done. But I can though expand the unity operator with a bijective operator J, such that the inverse exists and it results in unity again. So I can do that mathematically. This is not physics, this is math. I'm allowed to do that. And the next part is now an interpretation. I can just set these brackets differently. And I can set the brackets so that one part of it is a new lensing operator, and the other part is a new source. And so this is effectively a way to describe that I can find different shapes in the source with a different lensing operator to result me the same image. Because there is no clear distinction, I can always introduce unity, and it can just reassign shape and distortion freely between the two. And the only requirement is that whatever J is bijective, and so it satisfies that all the in and output are the same. So that's the general way of defining shape noise. So that is even allowed beyond the linear regime. So can even non-linearly distort it with a certain region, as long as there is an inverse to it. So that is basically here the statement. And in the literature, this type of generalized degeneracy is known as the source position transfer. The name is not so accurate, it's a bit historically motivated, but that's basically a mathematical form of it. So that's a bit the math, and you can define, you can even write down that J inverse here and J are effectively the E1, and in that case, so happened the negative sign for gamma. It's nicely been shown, found out by, I think it was Oleg. So that's one single image. So very limited information. This is basically what weak lensing can do, but with a lot of sources. But what if we have multiple images? So strong lensing, that's what the course is. And so I want to go into this regime and talk you through the same. So when we have multiple images, so if we don't have multiple images, we are basically, the statement here graphically between what I told you is we can have different shapes of the source and different lensing operators, and I end up with the same image that we see on the sky. But now when we have multiple images, we have a crucial property of strong lensing, that these two images must come from the same source. So I cannot make a lensing operator here that from a source that looks completely different. So whether I choose S or S tilde, we need to have relative lensing operators L1, L2, or L1 tilde and L2 tilde that actually match the relative shapes and positions on the sky. And that's the crucial part where strong lensing with multiple images really add significant information that we can make use in our advantage. Even though we don't know intrinsically how the source looks like, we have twice the same source on the sky, and that arrow here from the right to left or left to right, these relative lensing operator, that is independent of what the intrinsic source looks like. So we can measure this operator here. That's the statement here. And here is the math. Basically, yeah, you can make it D1. You can go from one image back into the other image, and you can go through L2 tilde or L1, you end up with the same other image or the relative mapping. There's also a bit biased. Here's a link to work that goes a bit in more detail, which also this text is basically copy pasted and gives a bit, and also Jupyter notebooks from this paper where there's some examples if you're really interested in this type of degeneracy and what assumptions can break them, etc. Are there any questions?
Yes, please.
Yeah. Mm-hmm.
What about mapping between the sources?
You mean between S and S tilde?
Yes.
And this is not, so in this, what we can measure here, there's no need to know anything whether we go through S or S tilde. Because the L2, L1 inverse is the same as L2 tilde, L1 tilde inverse. So there's no access of mapping between the source, or basically between the source needs to correspond to a mapping in the inverse in the lensing kernel to get the same image.
Okay, because at the end I mean, if I am understanding well, you in the image plane, you are going to obtain the same image independently of the sources because the mapping L or L tilde, right?
Yes.
So I was wondering if in the case of the sources there is some kind of I mean, because I understand that it's independent of the source, S or S tilde, you are going to see the same thing, right?
Yes.
So that's why I was wondering if there are some equivalence between the different sources that can be able to reproduce the same image we're observing.
So for the same, I mean, the equivalent statement is basically this guy here. Between you can find different sources that are distorted in one way, and you distort the lensing kernel in the inverse way. That's always possible. That's basically also the exercise we've done here, if I understand you correctly. What I'm focusing here is what we can actually observe, and what we observe is only in the image plane. Okay. And so the focus here is, if you see two shapes in the image plane, what can you actually tell independently of what you don't have access to? And that's this operator here.
Okay, so in order to say something about the source producing this image at this level, you don't know.
Yes. Yeah.
Which the real, I mean, the real S.
Yes.
Okay.
And one thing also, like overall, I can always displace the deflection field by an arbitrary angle, and actually on the sky normally, where we see things that are in cosmological distance, it's often displaced by several arc seconds,
okay,
or even arc minutes. We just don't have access to that displacement vector. So often it's actually misleading if you say lensing is just, you know, coming here and then slightly deflected. Normally what's happening is basically something like this. Right? And what we only see is the differential between two rays coming close. But overall, where the actual source is, whether it's left, right, top or bottom, we don't have access to.
I understand. Okay.
Yeah.
Thank you, sir. Yes.
Where you see things on the sky, it's not where it actually comes from.
Yeah.
Yeah. Any other questions so far? Otherwise, for now, we go in another example, and here we start looking really more into strong lensing. And this is the MACSS sheet degeneracy. Raise your hand if you have heard the term. It's not about whether you understand it, what it is, but whether you have heard of it. Just wonder. Give you some time, at least 2 people raised their hands, so at least it's partially known. It's definitely worth introducing. Thank you. So what is the MACSS sheet degeneracy? The MACSS sheet degeneracy is effectively a special case of the overall degeneracy operator J in that language that I've used here. And effectively the simplest operator J that has an inverse is a scalar. So you can multiply by a number that is non-zero, and then you can divide by the same number. And so you can use the operator J just as being a widening and shrinking of the overall mapping. And that in that term is the mass sheet degeneracies. That's all it is. So what happens so is that for this degeneracy, that scaling, there is a more physical interpretation of what may go on if you add such a degeneracy plane. And what happens here is mathematically in the lens equation, beta equals theta minus alpha, you multiply both sides by lambda. And here what I did is just extending I added a theta, I extended by a theta, such that I can keep the same lensing equation as before, and adding this term here. And if I now differentiate it in terms of convergence, the equivalent is written here, which effectively means that this transformed distortions corresponds to the same profile that I had before, whatever it is, scaled by this lambda, by this scalar, minus this constant here. And this constant effectively is a constant sheet of convergence. And that's where the name comes, mass sheet degeneracy. So you can think now, not just in J of a scalar adding and whatever happens, happens. You can think of it globally, that whatever you had previously as a model that you think may be viable, you can add a sheet of mass and subtract off or lower the overall previous profile, or the opposite, you can actually enhance the profile and subtract off a convergence sheet. So that is this specific degeneracy, and that's one of the major limitations for time delay cosmography, for example. And the reason for it is, you may want to do this exercise, is you can compute the time delays under this transform, and they're not the same. They're scaled by lambda. So you can find a lens model that fits. You can transform it through these components. You still get the same observables, where the images are, how they are relatively distorted, but the time delay prediction is different. And that can be an issue for time delay cosmography. So, and in the next block here, we're going to experiment with this degeneracy. And this is a bit a larger block. Some of it you may have seen in the previous block, but we're gonna, in short, gonna simulate strong lenses with different mass sheet degeneracies. The images gonna look the same, but the lens model is gonna be different. And I'm gonna walk you through this box here, and then you can also play around with it. So are there any questions for now? No. So then I walk you through here, and please interrupt me if you have questions. So the first thing is very similar we had. So we introduce a lens model, which in that case, we do a singular isothermal ellipsoid, so an elliptical mass distribution. And we add a convergence, which we can use to mimic this mass sheet transform here. So this is a two-component model. And we start here with just an Einstein radius of 1.5 arcsecond, a bit of ellipticity. These E1 and E2 are basically our mass density, but it's the same definitions as for the light ellipticity. And we choose the center of this lens to be at 0, 0. And to start with, we don't add any mass sheet. So we set this guy to 0. We here, to compute lensing observables, we also add a light profile. And in that case, for simplicity, we add an elliptical Gaussian. So it's a bit more realistic than an ellipsoid of constant surface. So here I choose an elliptical Gaussian with a certain 1 sigma radius of 0.1 arcseconds. with some ellipticity and happen to place them somewhere in the source. So this function here is effectively performing the MACSS transform for these choices of models when we add a certain lambda scaling. And so what it does here, it scales the Einstein radius by a lambda, and the Einstein radius is the component here that dictates what the convergence actually looks like. So it's overall scaling. That's this guy. We add now a MACSS sheet with 1 minus lambda. This is this guy. So we have done the lensing transform with these two operations. But now what also changes is the source position. So everything that we see previously at the source coordinate beta, we see at lambda times beta. And this source transform is the next block here, scaling of the source side. One thing that scales is the size. So this is the width of the Gaussian. We scale with lambda. And the other is the position of the intrinsic source, which is also scaled by lambda. And so what is returned here are also keyword parameters. You can print them as well that just happen to have different parameters. So it corresponds to a different physical model, different source position. So the next thing is basically the same old that we've done before. We define a grid of where we want to see the surface brightness on the sky. The next thing here, we evaluate the surface brightness without the MST. So we reshoot the original lens model back in the source plane and evaluate the surface brightness in that case of the Gaussian at this case. And that's it. The next is here, we use an MST transform. I just happen to choose a quite significant one, 0.5. Here I transform these guys, which is this function, and then do the same thing. I reshoot through this transformed lens model, get different coordinates in the source plane. So I give them a different name. And then here I evaluate the transformed surface brightness profile, so scaled and shifted. And I get the flux of the image with the MST. And here I do the plotting, which here I just plot the flux of the image and flux of the MST, and also the lens model corresponding. And so if I execute it, you get what you probably already see. And you have two lensing objects. You see 4 images appearing distorted here. They look not just by eye the same, they're actually identical. They're mathematically identical of how they look. But when we now look at the lens model here, we note a couple differences and some similarities. Similar or identical are the image positions. So nothing on the sky has changed. So the positions are exact, the relative positions are exactly the same. The relative magnifications is exactly the same. What has also not changed is the position of the critical curve. So this is also on sky, this is exactly at the same location. But there are a couple of things that change. One that has changed is that the diamond boxes have grown here and they correspond to the absolute magnification. So absolute magnifications have changed. So, that's one thing. Another thing that has changed is the caustic has shrunk here. So we have rescaled everything in the source plane. And what has also changed that the star, well, it's currently already quite close to the center, has actually been moved. So the source has been rescaled. And another thing that has changed is you see the gray scaling with the MST here. This is more gray than here. So this is the additional MACSS sheet in the conversions that changes. These are the changes, while when you just see the lensing, you cannot distinguish between these two components. Any questions so far? So what I now suggest you to do is play around with this lambda and see what's happening. So one thing you can do is if you set that to 1, then the transform is the identity and you effectively get exactly the same lens model out. You can go 1.5 in the opposite and see what's happening. And you see effectively negative convergence, how the caustics blow up, but the observables are the same. So I want to give you 3 minutes, play around, and please ask a question as we go.
So Simon, probably you're going to explain this, but if the observable plane basically remains the same, it's identical, how do you use this mass degeneracy, this shift, the degeneracy, and like in practice? So I'm having troubles to understand. I mean, conceptually and mathematically, it's understandable, but from observationally, I don't see how you use it.
So it's not, well, using is probably the wrong word, but being cautious about it.
Okay.
Meaning that when you find a model that fits, you have to be aware is that is a set of other models with different certain physical interpretations that do also fit.
I see.
And so you have to be cautious of how much you want to rely on that single fit that you have on the assumptions. So in that sense, it's not really making use of it directly, but you have to be cautious about it.
Exactly.
And one thing,
Okay.
yeah, and one thing to mention, so if I really want to know, okay, is this the universe we're living in, or is it this the universe we're living in, or at least the lens that I'm staring at, that I want to learn about the universe or astrophysics? There are ways to do this. First, just to start, some of these transforms are really in a regime where they become unphysically, or where I can clearly state that physically this is not really plausible. For example, such a transform needs to very negative convergence. So you have to have negative mass. So you can go below convergence of 0, which means, just to know, convergence equals 0 doesn't mean actually 0 mass. It means background density, that the metric is not distorted. So straight lines of the rise, and the background has mass. And so you can reduce the mass below the background. And in fact, a lot of lines of sight are below background. And so they have slightly negative convergence. So that you can do, but you have a limit to how far negative you can go. At one point you hit the FLRW metric. It does not allow you to that. So there are regimes where you can clearly say this is not physical, and this regime here is in that part. Mathematically still possible, but cosmologically, physically not. So that's one thing. You can argue that certain also the shapes. So at one point it needs to go to 0 convergence, and so a full mass sheet that in mathematically extends to infinity is not a physical thing that the universe exists. All the mass profile eventually need to go back to the background. So that's the homogeneity of the universe, and that's how we, can do cosmology. So that's one aspect. So there's always only approximated mass sheets that are actually physical plausible. So that's one thing. And so but if I'm now in the regime of, say, 0.9 versus 1, and want to know, okay, can I distinguish these two guys? Then I have the means to distinguish them. One is stellar kinematics, or any other property that relates to the physical 3-dimensional mass of my deflector, because the physical 3-dimensional mass of my deflector is different in these two cases. One is 10% more than the other. And so if I have, for example, stellar velocity measurements of how star orbit in this potential, I can distinguish at least to a certain precision between one and the other model. And that's the main approach we've done or have moved to in the TD Cosmo collaboration. So the latest results rely effectively on the stellar kinematics to distinguish models of these types of families. So that's one. And other one is the absolute magnifications of the images do change. So if I know something about the absolute, or not the absolute, the unlensed source, say apparent magnitudes of supernovae that are standardizable, and if I measure the flux that when it has been lensed, I can relate how much actually the lensing does in terms of magnification. And that allows me also to distinguish between the top and the lower panel. And these are two ways we can do that. Currently, we're mainly focused on stellar kinematics because that's what we have most. But in the near future with LSST, we're going to have a order like 40 to 50 lens supernovae, and if we can follow them up, 40 to 50 type 1A supernovae. There may be others as well that we can also use as standardizable candles. We don't need to have a full standardized measurement to measure H0. We just need to know what is the expected apparent luminosity in the absence of lensing. That's basically the knowledge we need. So these are the two avenues we can actually break. And it's also so this is for Hubble constant measurement. So there it's directly, it changes the Hubble constant by 10%, depends on which model I pick right here. For substructure dark matter, this is less of an issue. And the reason is a smooth mass sheet does not really change the granularity of the lens. And if you're only interested in, say, you know, how granular the lens is, we don't really care too much whether this is the global model corresponding to it or the lower one. So it really depends on what science case you're doing, of whether you actually need to care between, you need to distinguish these components, or whether you can work with other, yeah, you don't have to care or can marginalize over it. Are there any other questions? I know it's a lot. Also, like we just started an hour ago, and now you basically, in a few lines of code, put in some Einstein rings out. Also doing degeneracies, shear, ellipticity, distortion matrix, all of it, a lot of in there. So I'll suggest now, and I think you had also a lot of classes, we take a break, 15 or let's say until 9:25. So definitely more than 10 minutes. Use it, whatever, take a break or rerun the notebook, whatever you and your body feels is mostly needed. We come back at 9:25, and then we start the last notebook, and that you have a glance on. Yeah. I stay on for some questions, but yeah, feel free to zoom out, literally.